So basically, um, we have seen these are the points basically we have discussed previously, like the in during model compilation we have to specify the loss function, what I was saying. For example, here just two loss function I have given, mean square error and cross entropy, or maybe something more. For example, example of optimizer Adam SGD. The full form of SGD is stochastic gradient descent. Okay. Define the evolution metric. Evolution metric can be accuracy, can be F1 score. Okay. So all these are options for those different parameters. You can give when you are going to compile the model, and you have to use the compile function. Already you have seen. Then you can do the you can use the fit function. You have to use the fit function for training the model, and then you can monitor the training progress with callback. What does it mean? It means that I will show you, maybe try to show you it's by some code in next day, that there will be a situation, maybe you will see that you have started training the model, and models train well, like as the epochs increases, the accuracy of the model started increasing. But sometimes what happens is that after a particular time instant, or after a particular set of epoch, or because of some reason, if you continue the training, the accuracy suddenly started decreasing. I mean, when at the first time model has started training, maybe accuracy was very low, and as we continue the train, the accuracy increases, and at some point of time maybe accuracy become 87%. For example, after some set of epoch, maybe it happens that this 87% started decreasing again, like 86, 85, like that. That mean maybe, or maybe another thing can happen, that already we have seen in the last day that we can divide the whole data set into three parts. One we call train data set, one we call validation data set, and one we call test data set. Among these three data sets are part of the whole data set. But these three data sets, I mean subset, are not, you know, like anyhow um, are basically, I mean, they are all mutually exclusive. That means if you say that if you try to make a Venn diagram for the sets, like you can say that if this is your train data set, it will be your test data set, and it will be your validation data set. It's not possible to have a single you can say, what is not coming in my mind, that the two sets cannot collide each other. Okay, something like that. So you have divided the entire data set such a way. It happened. Okay, it is the ideal situation. Now, what is the difference between validation data set and test data set? See, the validation and test data both are basically used to test the model, not training. For training the model, we use train dataset. But the difference of validation dataset and test dataset is that the validation dataset is used to test the model performance during training. Okay. And test dataset is used to test the model's performance after the training is over. Okay. Just like, for example, you are uh, say for example you are trying to teach trying to I mean um, uh, say for example understand a particular subject. Say for example you want to learn data structure, so you are reading a book and you have set of questionnaires. So every time you are actually reading the book, you are trying to solve the questionnaires. Okay, which is basically uh, you know giving you an idea that how good you have learned at the intermediate learning stages. In this way, after you read the whole book, your learning is over. Then your actual examination will start, and that actual examination question paper is the test data set. Something like this. Okay. Now, sometimes what happens is that your accuracy is increasing for trained data set, and also accuracy of validation data set is increasing. Fine, very good. Suddenly, it may happen that your accuracy of the trained data set is very high. That means the model is very good on the trained data set. The predicting the output of the model is very good with respect to the trained data set itself, on the data set with which you are doing the training. But the accuracy on the validation data set suddenly started decreasing. What does it mean? It's a scenario which already we have seen few classes back. That is what we call, you know we call over I mean overfitting. So we are overfitting the model with the trained data. That's why we are not able to you know predict the data of the validation dataset with a considerable amount of accuracy. So the point of training time when this started happening, that accuracy of the uh, model with trained data set becomes extremely high, and accuracy of the model with validation data set started decreasing. This particular time is the time which is the best to stop the training, because if you continue training the model, what will happen? The model will be updated by some new weight, and based on that it will show a very good accuracy on the trained data, but when you will test with test data, you will see accuracy is 40%, because model is overtrained, means overfitted. So I should stop the training at that point. And that is what is possible by what we call early stopping. Maybe we have set the model to train 1000 epoch, but after 400 epoch, say we have seen this kind of pattern, that accuracy of validation dataset started decreasing. So during this point, if you don't stop the model training, then the model will basically go to some failed model at the end. So you should immediately stop the model before it continue and go up to 1000 epoch. And that is what we call early stopping. That's why the name early is given. So you are stopping the model, not you are not continuing the model till the end of the end of what you expected. Before that you are stopping, so it's early stopping. And how we can do this? We have to use a specific type of method we call callback. So we will see this callback also. We have to find out a scenario. Actually, I have to find a scenario for which that this kind of situation happen, right? Unless it will not be very visible for you. That's why I need some time. I have to write some code for that. I have to create some scenario where this type of situation is happening. Then it will be more visible to you that what's basically happening and what is the effectiveness of this callback using early stopping. So these are things that we can do. Okay. So any question till now? Very good. Let's continue. So Anyway, I'm not going in detail of the real world applications using computer vision and natural language processing, because this is what basically we are going to explore in later, because this is the part of the you can say deep learning architectures, so we will see that later. But before that, let's continue with a multi-layer perceptron with Keras, and we will come back to the dataset again, the iris dataset. As you can see here, that see this is a flower, okay, a flower, and these are the three categories of flower. And based on the category, it is given iris versicolor, iris setosa, and iris virginica. Okay, and there are some. This is called a sepal, and this is some petal. It's some biological, implication. Maybe there is some biological implication, but we are computer scientists, so maybe we don't need to deep dive into exact biology right now. But we can see this is as a feature of our data set. Okay, so what is the width of the sepal? What is the width of the petal, what is the length of petal, what is the length of sepal, can be utilized as a feature in these data. And based on that, the dataset is created, which is representing something like this. See? So the sepal length, sepal width, petal length, and petal width. Okay. So for specific iris setosa type of flower, we have a specific pattern of these four features. For iris versicolor type of flower, we have another set of pattern, another type pattern of these four features, and also for iris virginica, we have some pattern. See, that means you can say according to this data set that each and every data point is basically four dimensional, right? Because you have four features. So with respect to a computer scientist, for you, for us, this iris setosa is a four-dimensional input vector. That's all for a multi-layer perceptron model. So if you just try to map like what we have just learned few slides back, if I want to create a dense layer, okay, a multi-layer perceptron, our input layer must have four dimensions. So when you will call the model.add function, and within that when you will call dense function, the in the dense function input underscore dim has to be 4. That is representing the 4 inputs, which will capture this 4 components of this vector, because it's a vector of 4 dimensions. And then you can num units, the number of neurons in the second layer. You can be 10, it can be 15, it can be 3, it can be in your and as your choice, that's for sure. Okay, so basically we can go for the classification model design steps in this way, just like I have written here. So let's go through one by one. So we can start by importing the necessary libraries. As we all know that we need some other libraries to import the data, and pandas is a very crucial library for us, which is going to useful for us to store the data, maybe present in some CSV file or something like that. Okay, and also maybe we need to some numpy object, numpy class, numpy package for some different type of mathematical operations, and we require the Keras package. May not be TensorFlow, maybe Keras. Okay, so and you see there is some already function load underscore iris, which is present in scikit-learn package under dataset folder. Under this we have lot of different publicly available datasets, lot of, not only iris, you will see there are a lot of publicly available dataset which basically present in this scikit-learn datasets. So for our practice, you can take help of any dataset, and you can try to create model with the data set. Okay, so and if you see the features present, obviously these four features, and the target labels will be the species, the type of flower. Okay, so see, like we can split the data set into two part, training and testing, and we have, that train test split is there, which basically splits into two part, and the percentage of data you want to put for training and testing, that's your choice. You can put by the percentage by some 80/20. Mostly it is used 80/20 or maximum up to 70/30%, means 70% for training, 30% for testing. Okay, so I mean, accordingly, basically what we can do, the first thing that we have to do is basically feature standardization, which is a very standard practice for any data set on which we work. It's not about only iris data, because you see, iris data is a very straightforward data set which does not have much level of complexity. That's why maybe if you don't standardize the data in iris data set, you will still get a considerable amount of accuracy. But in future, the different data sets, the practical scenario that maybe on which we can work, may not be that level of easy or to interpret. So that's why in that case standardization might be very much crucial, and that's why it's always a good practice to standardize the feature, to have zero mean and unit variance, because we all know standardization means, the if you have a data set having some distribution, obviously, right, have a data set, like for example, if you see that, if I go back to the data set here, the sepal length, see, the sepal length for all the different type of flower have some particular value, you see, 5.1, 4.9, 7.0, 6.4. So in this way, total number of available row is 150. Okay, 50 for every class of flower, and we have three class of flowers, so 3 into 50 means 150. So that's why 150 row available, publicly available. So in this, that means 150 values available for sepal length, similarly for other features. Now this 150 value of sepal length, if you just put 150 values of sepal length of the from the dataset, it will create a distribution, some statistical distribution, right? Right. And what is the purpose of standardization? The standardization means that the distribution that you will get based on the raw data that you have available, that you have, it basically, the equation of the standardized function, you know transform these values, all these raw values, into another set of values, such that the mean of the value becomes 0 and standard deviation become 1. If you see, the mean of the 150 values of this sepal length, it's definitely not 0. It's maybe, say for example 5.3, and standard deviation is 0.4. Maybe I'm just giving you an example. Okay, maybe in case of sepal width, the mean is 2.9 and standard deviation 0.4. So see, try to understand, the if you just give the raw input into the model, the and this sepal length is going to a particular input, say for example, just I'm trying to say is that, so for these four features you have four input layers in the right, so four input layers, and these input layers here I am giving sepal length. In this input I am giving sepal width. What is uh, the value that I am passing in this input layer is with mean 5.1, standard deviation 0.4. Whereas the data that I am feeding to this next neuron is 2.9 with standard deviation 0.7, for example. So just if you compare the value that I am passing in these two neuron, the value in this neuron is higher, right? So that means the neuron in the next layer, which is connected with both these neurons, obviously this neuron is getting some more value. There is a possibility, there is a chance to be dominated by this neuron in this particular summation value, because the value that I am getting through this neuron is always higher than the value here. That means there is a chance to get more biased weightage on a particular feature, but as a during learning it is not expected. We always should have a same weightage on each and every features. The feature should have same weightage. I mean features in the sense, I should say that the feature should have same distribution. Which feature will have more weightage, that should be decided by the W present associated with the connection, not the feature value. That is why if you convert the first feature, if you standardize the first feature and also standardize the second feature, I mean actually standardize all the features, what will happen? This sepal length will be transformed, these values of sepal length will be transformed into some another set of values, such that the mean of the sepal length will become 0 and standard deviation of the sepal length will become 1. Okay, so that means right now the maybe for sepal length it is something like this, say for example like this, where this value is say for example say 4.8 and these value say for example 7.3, whereas the sepal width maybe have a situation like this, whose minimum value say 2.8 and maximum value maybe 3.5, something like that. Just I'm trying to say, definitely this in this two distribution dominate this one, which should not be expected. So if you standardize all these features, what will happen? This particular one will be transformed such that the distribution curve remains same. Instead of mean something, say for example 5.5, mean becomes 0. Similarly, this one also, the it remains same but mean becomes 0. So if mean is 0 as standard deviation is 1, the first standard deviation is 1 with similar thing like this, so that means what I can say, the distribution of both features remain in the same platform. There is no difference in the values. So there will be no chance to dominate one particular feature over another feature by its values, which will create an unbiased learning, and that is what should be our goal. And that's why standardization is so vital, for any complex data set. So this is the scenario. So that's why this standardization is very important. Just what we have seen here. So we have again different predefined functions we can simply use for this pre-processing for standardizing the data, and then we can start working on defining the MLP models. Just like already I have, you know, said it many times, so I'm not going in, repeated the same thing, it will be boring for you. So just like already we have seen, we can use sequential function for creating models, and then use the add and dense function for creating the layers with the number of neurons as per my choice, also the activation function as per my choice, and then we have to do the model compilation. Then in model compilation we have to choose the loss function, maybe sparse categorical entropy or maybe something else. But specifically, if you say this sparse categorical entropy is very good for a multi-class classification problem. That means in this iris data set we have multi-classes, not two classes. Multi-class means more than two class. If it is two class, you call binary classification. More than 2 is multi-class. If it is 3 or 4 or 10, doesn't matter. So for multi-class classification problems, sparse categorical cross entropy is a very good option to choose as a loss function. We will see this, and also optimizer Adam is very good, and also we can choose accuracy as the metric, and then we can start doing the model training that already we have seen using fit function, where we have to give the training data set, that is the set of inputs and corresponding set of outputs, and based on that the training will be done, and also we have to give the number of epoch that I have said. So currently we don't have any callback, so I will try to implement the callback with some situation, creating some scenario, so that it will be visible for you to understand what is the necessity of a callback. And there is one more parameter present in the training function, which is verbose. Verbose equal to 1 means actually the progress of the training gets displayed. That means how much epochs is completed, or during the completion of the epochs, what is the metrics, what is the the accuracy in the validation data set or something like that. If you don't want to see the progress of the training, you can keep verbose equal to 0. Okay, and there is another option, verbose equal to 2, which gives much more detail. So we will see, keep considering for different verbos what is the output that we can change, we can see during model training. Okay, and also we can see the the model evaluation on the test data. So by which the model dot evaluate. Okay, evaluate means actually it is not predict. See, predict means it will give only the output, but evaluate means it will give output, and based on output it will give the accuracy. So that's why the evaluate comes. Okay, so it gives the accuracy, and then if you want to go for only prediction, then you can use model dot predict function with the test data set. That's all. Okay, so and then you basically try to create the accuracy score based on another function, again a predefined function within the scikit-learn package, and the function name is accuracy underscore score, where within this function you have to give the actual predicted actual output, that I mean actual output of the test data set, that is y test, and the predicted output that you got based on the test data input, test input data. So predicted output based on the test data set is given, say for example, y pred class. Just for example, I have written here. Okay, and this accuracy underscore score, this function is present within the packets sklearn dot metrics. So if you want to utilize this accuracy underscore score function, you have to import this thing. So you can write like from sklearn dot metrics import accuracy underscore score, then only you can directly use this. Okay, so these are some things basically we can use using this model, I mean calculating the accuracy. So now it comes that we have some functions, we will let's do one thing. So now let's do one thing. Let's see how we can, give the inputs within as a parameters when we will call the model.compile function as well as model.fit function. So by the way, any question you have till now? আমি অনেক কথা বকবক করে যাচ্ছি, আমি বুঝতে পারছি। হ্যালো। Verbose is basically a parameter. Sorry, verbose is কোথায় গেল? Verbose is basically a parameter which used for, deciding whether you want to display the progress of the training. Like for example, you have chosen say some particular number of epochs, say 100 epochs, that model will get trained, and you want that after completion of every epoch you want to see what is the accuracy in the validation dataset. Because what epoch means that the whole dataset will get input, I mean gets fed in the model, and based on that you will get some output, I mean you will get some accuracy, right? Say for example, the IDs dataset. In the IDs dataset, say for example, I want to train the model with IDs dataset with say 100 epochs. What does it mean? First thing is that we have 150 column, sorry, 150 row. In 150 row, say for example, I have chosen to consider 80-20 ratio for training and testing. So 80% for training and 20% for testing. So that means 120 row for training data and say 30 row for test data. Okay. Now in this training data, some set of data, say for example, among 120, say 100 data I have kept for actual training and 20 data I have kept for validation. Okay. So now I have chosen to consider, I have chosen 100 epoch. Means what? It means 100 times this I mean not 100 epochs, say for example 200 epoch. It means that 200 times the, I mean the 100 rows that is kept for actual training of the model, fed into the model, get some output, calculate error, based on that backpropagation done, weight updated, and based on that locally trained model we are checking the accuracy by the validation dataset, right? The validation dataset say for example the accuracy of the validation dataset becomes 70%. That means after first epoch the validation dataset accuracy is 70%. It is epoch 1. Next epoch 2 comes. In the epoch 2 again that 100 data will be fed in the model, the same 100 data, again the same thing will happen. So basically, the things that I have said is basically 100 times repeated. Just like you can say that you are reading your book 100 times from first to last. So you started reading from first page, you are completing each and every page. Then at the end, you reach up to the end of the book. The whole journey is one epoch. Then again you started from the first page. Again you are revising. So your revision start. So that's the second epoch. Again, third time you are reading. First to last. Third epoch. So this is what epoch is. Now verbose 1 equal to means, say for example, I'm giving an example. That verbose equal to 1 means it will show the progress of the training with respect to epoch. Say after epoch 1, what is the accuracy of the model? What is the error, average error that still model is producing? This information if you want to see for every epoch, then you must have something for which you must have some parameter, right, by which you can represent that I want to see the result or I don't want to see the result during training. And the verbose is the parameter. If you don't want to see or don't want to display the progress of the training or the results, intermediate results of the training during training, you can keep verbose equal to 0. But if you want to see some result some progress, you have to give verbose equal to 1. That is my point. Is this clear? Any more question? Any more question? Okay. So now we can see how we, let's do one thing. Let's deep dive into the compile function and the fit function. What exactly different parameters is there in the functions, and then I hope the things will be much more clear to you. Okay, so let's go to one by one. So we'll start with model.compile. What is this? Model.compile function in Keras is a very crucial step before training a neural network. So understand it very carefully. It configures the model. See, it is, I'm saying it configures. So when you are calling the compile function, it means that you have not yet started the training. You are actually still working with the architecture of the model. You are preparing the model to train. Okay, so it configures the model. The configure is the best word actually. It configures the model for training by specifying various settings. So let's, what are the settings? So I have some important settings here just given. For example, optimizer. I just said you. What is an optimizer? Optimizer determines how the model weights are updated during training. Okay, so there are different type of optimizer available, and I have given three most important optimizer we very frequently use in our model: Adam, SGD, and RMS prop. Okay, and it's given the, also the full form is given. Adam means adaptive moment estimation. So SGD means stochastic gradient descent. RMS prop means root mean square propagation. So these are actually a short form of this different optimizers. So these are optimizers means actually these are, if you can easily Google all these things and you can see what exactly formula behind these optimizations. Okay, and it is written one thing that choose an optimizer based on your problem and experiment with different ones. See, a very important one, experiment. That means again I'm saying there is no specific rule book which can say that for this type of problem this particular optimizer has to be used. There is no rule book. And here is the beauty of machine learning, that you have to explore many things, and you can also say it's to some extent a drawback. Mean, since there is no rule book, that means the your model, which model is the best one, that will depend upon how exhaustively you have searched different parameters. For example, I'm telling you, as a situation, I'm telling you that say you are taking these three, you are using Adam optimizer, SGD, RMS prop, all these three one by one in your model. Okay, and based on these three, for example, Adam is giving the best result. Okay, so you can say that your model gives best result with these settings, but you cannot claim that your model will give best result ever. What does it mean? It means that you have checked with these three settings, but other than these three optimizers, there are many optimizers available. Until unless you are checking the population, you cannot claim that that particular optimizer is the best one among the population, right? Because you have not checked the populations. You have checked some samples of the population. For example, there are 10 optimizers available in market. Just for understanding, I'm telling you. Among 10 optimizers, you are checking these 3 optimizers, but 7 are left, which you have not yet checked. So without checking those 7, all 10 optimizers, there is no way to claim that Adam is the best optimizer for your problem. right? I hope you can understand my point. So that's why what basically always we write, based on the settings or different settings we have chosen, we say that based on these settings, this set of settings, this particular settings, some particular settings giving the best accuracy. But we never claim based on the settings of, based on all the settings, it is giving the best result, because you have not yet checked all the settings. Okay. Next come to the loss. Again, as I told you, loss function is again very important. For example, for example, sparse categorical entropy or categorical cross entropy, which is suitable for one hot encoding class labels. But this is for classification. If you want to go for regression, maybe mean square error are very common for this considered as a loss function. So again, the which particular loss function you are going to implement or you are going to utilize in your model depends upon the problem. So day by day, once you will get more matured of using these different loss functions and different settings, you will get more versatile to decide which particular settings you should use in your case. Similarly, again, if you say matrix, you know what the different type of common metrics are to decide the, the accuracy or something like accuracy of the, or not accuracy, I must say, the goodness of the fit of the model. That is either accuracy or precision or recall or F1 score or mean absolute error or mean square error, or sometimes you also got MAE, what is nothing but MAE means mean absolute error. Okay, so these all are actually different common metrics which we use to evaluate the performance of the model. And also say for example, there is another one which is run eagerly. If this is true, the model runs eagerly, like instead of using a graph. So it's we don't generally use this run eagerly uh, option in the compile function. So remember, all these things that basically I have written, metrics, run eagerly, loss or optimizer, these are the parameters present within the compile function. Okay, so for example, some other parameters are also present, but one thing, always remember that you can run this model.compile multiple times to change the settings to fine tune the model. Okay, so like for example, different settings you can use. Say for example, you can use say optimizer Adam with loss sparse categorical entropy, or optimizer Adam with categorical cross entropy, or maybe optimizer Adam with mean square error. So any combination of these optimizers, loss, matrix can be used, and that is the part of research, that which combination of the different parameters is the best for your model. Okay, and that is what actually written here. That remember that you can run model.compile multiple times to change the settings or fine tune your model, and it's essential to configure these parameters appropriately for successful training. So it's very natural, right? So now if I go for model.fit function, just like model.compile, here it comes for the training part. Till this moment we are in setting up the model. Now we will go for the training part, and that's why it is written that model.fit function in Keras is used for training a neural network model. Now we are go for training, and it's a crucial step where the actual training happens. So if you see what is there, what are the different parameters we should pass when we call this fit function, you will see that first thing, the very two important thing without which it is not possible, is x and y. What is the input and what is the output? That's as simple as that, right? Now, what basically we pass? Your x can be, say for example, a numpy array or a list of arrays, or maybe a TensorFlow like a data set, something like this. Okay, so we will see how we can utilize this, and also target can be a level, or can be some number of samples or something like that. Okay, or maybe for a classification task, it can be a encoded data or something like a one hot encoded levels or something like that. So why can be, combination of multiple values as well, okay. So and now the next is, see, batch size, just what I was saying in previous previous slide. I hope you already have a knowledge of batch size clearly. So I'm not going in detail of what exactly batch size is, but you just, if I just do some points, what batch size is, it determines the number of sample processed per gradient update, like as a whole. Larger batch sizes may lead to faster training but require more memory. Because why more memory? Because they have to store the errors, right? So if you say a batch of 100, it means 100 errors at a time has to be stored. Then accumulation of the errors will be happen. Then based on that, the back propagation will happen. Instead of 100 batch size, if you say you have batch size of 1000, that means 1000 errors has to be stored instead of 100, and then the accumulation of the error will start. Now, obviously, storing 1000 errors at a time will take more memory than storing 100 errors at a time. So that's why it requires more memory. But it's given that, as I was saying to you, that smaller batch size provides more frequent weight update but slower training becomes slower, because for every small batch size, I mean, as number of batch size increases, the number of backpropagation algorithm will also increase. So the the I mean forward pass and number of backward pass will increase. So naturally it will create more training time. Okay, and then comes epochs. Again, this is very known word to you, I hope. So again, you can say that, like, you can also decide based on your power of your brain, that you need to have 10 times, you need 10 times revise of that particular subject you want to give exam. Maybe some other person need not 10, maybe 20 revise. Maybe another person need only 5 revises. So person to person, the number of revises vary, right? Similarly, here also the number of epoch may vary, and depends on that, maybe the training will get varied. The accuracy of the model will be varied. But obviously it has to have some threshold, not more than that or not less than that. Okay. So and also, as I told you, validation data, again, it's a part of training data on which basically the the evaluation of the model, the temporarily trained model is done. And you see, in the last point it is given, helps prevent overfitting, and this is actually the main purpose of validation set. And that's why it is written, see, evaluate, I mean, used to evaluate the model's performance on a separate validation set during training. Means the model has not trained enough, maybe. But using the validation set, you are actually keeping a track. You are tracking how the model performance increasing. Okay, that's why validation set is very vital. And also it prevents overfitting, you can see that. And to prevent this, we can use callback. So you will see that later. Just like what I said here, callback again came here. So again, what I was just saying, that callback, a list of Keras callback functions available. Callbacks allows you to customize the training behavior. For example, what we just discussed few slides back, that early stopping or some checkpoint or some logging, and also common and some common callbacks as this. Okay. So anyway, we don't have any. I don't have any use case of callback as of now, but I will try to show you callback in future. Try to get some scenario so that it will be easier to visualize. But one thing is very important here, yeah, which I forgot to tell you, that is shuffle. Shuffle means you have a data set and you want to train. Better that you shuffle the data randomly, so that you don't get some specific outputs, at a time. Not at a time, I mean, one after another, you can say. Like, for example, you have a data set of three classes, the mm, uh, iris data set. Okay. And say, for example, you have 100 rows which is used for training. These 100 rows will have some set of rows, say for example 30 of a particular class 1, 30 of another class, and 40 of third classes. It is also possible that the data set in such a way that the first 30 data which will be input to the model during training is the class 1. Then you are feeding the next class, the next 30 data having class 2. Then you are feeding next 40 data having class 3. This is also possible. Practical, I mean, ideally there is no error, but if you do like this, just try to understand practically what will happen. It means that you are teaching someone with some specific output for long time. Suddenly you are changing the output. Again, some long time you are teaching someone with some specific output. Suddenly you are changing the output, and again for long time you are teaching that guy with some particular output. So what will happen when you will teach someone with some specific output for long time? The that particular guy whom you are teaching will gets convinced with that type of input only, right? Because that guy have not seen the other data, because you are teaching with that particular input only, and that particular output only, like output of class 1. So naturally what will happen, that means the person to whom you are teaching is basically convinced with some class 1 type of data points. Suddenly you are changing the outputs, so it will be difficult for that particular person to train the second set of data, because it's already trained with some particular type of pattern. Now when you will feed some another pattern, suddenly started feeding some another pattern, what will happen? There will be a large error between the predictive value and the actual value that you are passing. I mean, actual output you are passing. Because the model has not yet seen that set of next set of data. Started seeing the first time. And now model has to change the weight again with that to make the performance better with that set of inputs. And again you are doing it long time. So what will happen? It will be difficult for the model to be habituated with any input. Instead that, if you shuffle the rows and if you randomly feed any one of these three classes, then after some set of time, the model has seen all these types of classes. So model will get sufficiently trained. Like for example, like, just try to understand model as a person. The model has seen all the different type of classes. It will be more easy for the model to, model will get trained more easily and will be useful for predicting the test. So that's why shuffling is very important. Okay. And obviously class weight should be there, but it is for the imbalanced data sets, so that also depends upon the problem, so it's not very always useful. So we can see if we can find some use case for this. And also there are some other optional parameters which sometimes we need to pass, but not very frequently. But last one, maybe it's very important. That just few slides back you have seen verbose, whose value I told you 0, 1 and 2. So 0 means silent, means no output, means that you will not see any output or any intermediate performance of the model during training. Okay, if you put verbose equal to 1, it means that it will show that during training the performance, the performance of the model is increasing with respect to accuracy or maybe the metrics. And if you see the verbose equal to 2, it means that one line per epoch, means that after a particular epoch it will show the result, something like that. Okay, so this is the three things with verbose, but verbose is not going to affect the training. It's just for you to see whether you want to see the progress or not. That's all. It's not going to affect the training part. So, and there are some other parameters, but these are really very, less used. But okay, but these are some parameters. We can discuss on this in future if we find some use case, but not very useful for today. So this is up to which. So this is up to which. Uh, we have seen that model.fit and model.compile. Now what we can do, basically, we have basically learned a lot of things using Keras, right? We have started with creating models using sequential function. Then we have seen that how to add the layers, specifically dense layers. We have seen that what are the different parameters we can pass in dense layers. We have also seen when what are the steps to involve from creating model till training the models. Specifically, we have seen what are the different parameters we can pass in model.compile and model.fit functions, which is going to be very crucial during model training, right? Now what we can do, we can go to some Python code, and we can see how we can utilize these functions for creating a model. I mean, a Keras based model, and create a very good model. So let's deep dive into the Python code, and let's see how we can run the code.